Hey everyone, Mr. Armitage here. In this video, we're just going to do a very quick look at what a chi-squared test for independence and chi-squared test for homogeneity looks like. All right. So you're going to end up with some sort of table for your data. Right here, I'm just doing 2 by 2 to make it simple. Okay, but these would be our observed values. Okay, so this one variable here, okay, 13 and 29, according to these two, right? It's a two-way table. Okay, you end up with the two-way table. Okay, now if you were looking at the test for independence, right, then you would say, variable x and y are independent of each other. Okay? If you were looking at homogeneity, you would say the distribution of y does not depend on x, or the distribution of y within these x's are the same, right? So this x could be like type of M&M, so regular milk chocolate, peanut, something else. Can't think off the top of my head. And then the y's would be the colors. And you would ask if it was homogeneity, right? Is the distribution of the colors the same? Because homogeneity is asking for the distribution across different populations. And is it the same in these different populations? Independence just means that you have two variables and you're asking, does one affect the other? Okay. So homogeneity, one variable, multiple populations. Independence, two variables, one population. And so basically, like, how many questions are you asking them? Are you asking different groups one question? That's probably homogeneity. Or are you asking one group multiple questions? That's probably independence. Okay, so let's look at what it takes to actually get the expected values out of this. Okay, so we have our observed values already. That's easy enough. And actually, I'm going to make this a little bit bigger just so we can see what is happening here. Okay, so with these, okay, the totals stay the same. So 42 and 36 here for the x's, and then for the y's, 22 and 56 for a grand total of 78. Okay. Now, you might remember from our probability unit, okay, if two events are independent, then their joint probability is just the probability of each one multiplied together. Okay. There's a lot of little subtle math to it, but ultimately what that means for us is that for each of our expected values here, our expected frequencies, okay, we take the row total, multiply by the column total, and divide by the grand total. And I don't have my calculator out. Okay, so 22 times 46 divided by 78. Okay, that gives me 12.97 right there. Okay, and then I repeat the same thing. So this one would be 22 times 36 divided by 78. Okay. And that gives me 10.2 2. Okay, normally you would use more decimal places, but in the interest of space, that is what I am doing here. Okay, so then this one, 56 times 42 divided by 78. 42 divided by 78. So that's 30.2. Okay, and we can already see, right, these expected frequencies here are pretty dang close to what we observed. Okay, so already we might have an inkling that these are going to be relatively independent. Okay, and when you do this one, you get 25.8. Okay, and now, right, the chi-square test statistic, it's the exact same thing that you had before. Okay, going to add together all of the observed values minus the expected values squared divided by expected. Okay, so we take, 13 minus 12.97 squared divided by 12.97 plus 9 minus 10.2 squared divided by 10.2 plus 29 minus 30.2 squared divided by 30.2 plus 27 minus 25.8 squared divided by 25.8. Okay, and for all of these values, you get, okay, so you get these values here for each of the contributions for each of these cells. Okay, you can see that this one has the largest contribution, right? This x2, y1 has the largest contribution to our chi-squared value, so it is the most different out of all of them. Same thing applies for goodness of fit, all of that. Okay, now we get our final chi-squared value of 0.245, which we can already know that that is not going to give us a statistically significant. We are not going to reject. We are going to fail to reject the null hypothesis, regardless of what degrees of freedom we have, because it's so small. Now that being said, okay, degrees of freedom for a two-way chi-square test, so homogeneity or independence, number of rows minus 1 times number of columns minus 1. So here we had 2 rows, right? y1 and y2. Those were our 2 rows. We do not count the totals. Minus 1 times columns. We had 2 columns because that was x1 and x2. Okay, so that's just 1 times 1, which is 1. We have 1 degree of freedom. Whoop-de-doo. Okay. Then we can get our p-value real quick, just so we can see what that actually is. So that's going to be chi-square CDF, where we're going to put in our value 0.245 as the lower, right? And then degrees of freedom as 1. So we go to distributions, right? I'm not showing that on the overhead thing because check out the other videos. Okay, upper value is positive infinity, 1 degree of freedom. There we go. Okay, this ends up being 0.621. Okay, so there's a 62.1% chance that we get a distribution this extreme. Okay, but if we used a significance level, alpha, of 0.05, okay, well then our p-value is much greater than that. So we would fail to reject the null hypothesis. So here, right, we do not have convincing evidence, or, yeah, we don't have convincing evidence that the distribution of y by X is different. Okay, so we don't have convincing evidence that the distribution of colors is different for each type of M&M, for instance, or that was for homogeneity. For independence, should have come up with an example for that ahead of time. For independence, let's say valedictorian or not is independent of living inside the Edison region or not. Okay, something like that. We do not have convincing evidence that living inside the Edison region or not, we do not have convincing evidence that living in the region is not independent of being a valedictorian, for instance. Okay, it's a little difficult to word it sometimes, but that's okay. You can always ask me. Either way, see you later.